Okay, guys, so we are going to go ahead and finish up lesson 4 here. So we're going to pick up right where we left off on page 53. Okay, so right here in the middle, kind of where it says fundamental theorem of algebra. So a polynomial function is a function of the form, and then we see this big, long, ugly equation. Basically, all these little a's, a0, a1, a2, and so on, would be numbers. So this might be like 5x to the 5th plus 2x to the 4th minus 7x squared. Things like that. We call that a polynomial. It says, as the theory of finding roots of polynomial functions evolved, a 17th century mathematician, Girard, made the following claim, which has come to be known as the fundamental theorem of algebra. So with a name like fundamental theorem of algebra, you can probably guess that it's pretty important in the world of algebra. And that theorem tells us that an nth degree polynomial function has n roots. So the degree is the biggest exponent. So the biggest exponent for a function tells us how many roots it has to have. Okay, so a root is a number that we plug in, and we end up getting 0. All right, so if I plug that value into my original polynomial, I would end up getting 0. Okay, so in order to think about that, I want to look at one of the ones you did yesterday. You don't have to turn to this page, but here I have a polynomial that doesn't have any x-intercepts. Okay, so looking at it, it looks like there are no numbers I could plug in that would make this 0. And that's because there aren't any real numbers. So up until this point, every number that you've looked at is called a real number. Okay, it's things like fractions, it's things like pi, it's things like the square root of 10, things along those lines. But there is another type of number that you have not been exposed to yet. So you can go ahead and turn the page to 54. Okay, so it says square roots can often be written in equivalent forms by looking for perfect squares that can be removed from the radicand. Okay, so you did this 2 days ago. So for example, the square root of 8 is equal to 2 square roots of 2, right? Because 8 breaks down to 4 and 2. 4 breaks down to 2 and 2. You have a pair of 2's that come out and one that's left inside. We can verify that the number 2 square root of 2 is equivalent to square root of 8 by multiplying it by itself and using the commutative property of multiplication to arrange the factors. So 2 square root of 2 times 2 square root of 2 ends up, you can follow the math there, being 8. So what we want to do is, if we allow, at least temporarily, square root of negative 1 to be a legitimate factor. Okay, square root of negative 1. This is not something we have seen before. So up until this point, you've always been told you cannot have a negative under the square root, and you can't when you're solving to get a real number. But here at this point, we're looking at something called imaginary numbers, where you can have a negative under the square root. So we will explore more of that idea with imaginary numbers, but in lesson 5. But for now, we want to just look at leaving a negative under the square root. Okay, so to show how we might represent negative 8 as a square root, we're going to think about some of these ideas here. So negative square root of 75. So I want to picture it just as if it were 75. So I'm going to come off to the side here, and I think we actually did this one the other day. So imagine it were just a 75. We would look at, okay, 75 is 25 times 3. 25 is 5 times 5. Okay, so I see I have a pair of 5s and a 3 left over. So this is going to be equal to, and I'm just going to throw the negative in there, negative 3 times 5 times 5, right, because it's a negative 75. So I've got a pair of 5s that could come out, and it would be 5 square root of negative 3. And that's how we're just going to leave it for now. So the only thing that's different is we have a negative under there. So we'll kind of build on that idea. Next one, the square root of negative 36. So hopefully a lot of you recognize 36 off the top of your heads as a perfect square, because 36 is 6 times 6. So we know this is equal to 6, but because of that negative, there's going to be a negative 1 left over in the square root. Next up, 32. 32 is not a perfect square. Let's break down 32. So I think about 32 as being 16 times 2. You could also do 8 and 4. 16 is then 4 and 4. 4 is 2 and 2. This 4 is also 2 and 2, so lots of 2's. So notice we have 1, 2, 3, 4, 5 2's. So this is the square root of negative 1, 2, 3, 4, 5 2's. Okay, so I got some pairs to find here. So I'm going to ignore the negative for now. So I've got a pair of 2's here that can come out. A pair of 2's here that could come out. So I'm bringing out 2 2's, or 2 times 2, so 4. Square root of, there's 1 2 left inside, and also the negatives left inside. So 4 square root negative 2. All right, last one here, square root of negative 48. So same idea, we're going to break down 48. So 48 is 8 times 6. 6 is 3 and 2. 8 is 4 and 2. 4 is 2 and 2. So I have 1, 2, 3, 4 2's and a 3. So I have negative 1, 2, 3, 4, and my 3. So now we bring out pairs. So I've got a pair of 2's here and a pair of 2's here that can come out. So when I bring out 2 2's, I'm really bringing out a 4. I've got my square root, and what's stuck inside are the negative and the 3. Okay, so this is very similar to what we did with simplifying square roots the other day. The only difference is we have a negative inside. In the next lesson, we'll take that a step further on what we then do with that in regards to imaginary numbers. Okay, so that's kind of the end of the new stuff for lesson 4. So we have some takeaways we want to write out just to kind of summarize what we looked at in lesson 4. So observations about the x-intercepts, right, where it crosses the x-axis, and the roots of a quadratic function. So first thing I want you to do, just to remind us of what a root is, I'm going to say that roots are numbers that, when substituted in the polynomial, make it 0. Okay, so if I plug in that number, I end up getting 0. Okay. Some other observations here. So if A and B are x-intercepts, the factored form is y equals x minus A times x minus B. Okay. And if you want, just for consistency, we called these P and Q earlier. It really doesn't matter what you call them as long as they're both the same. I'll change that to P and Q. We're also going to say square roots of negative numbers work the same way as square roots of positive numbers. And the last one, we're going to touch on that fundamental theorem of algebra. So the fundamental theorem of algebra says that quadratic functions, aka parabolas, must have 2 roots. Even if they don't have any x-intercepts. Okay, so even if our parabola never ever touches the x-axis, it still has roots. It still has values that you can plug in that'll make it 0. X-intercepts also do that, but sometimes there are numbers that aren't x-intercepts that are also roots. Okay, so feel free to pause there if students need more time to write that down. When you guys are ready, we're going to look at the next page here, page 55, looking at different types of numbers. So now that we've identified that these x-intercepts and roots can be different types of numbers, we want to explore what those different types of numbers are. All right, so our very basic numbers are whole numbers. These are things like 0, 1, 2, and so on. So if you were counting objects, these are the numbers we would use. So that's exactly what we say to describe whole numbers, as we call them. Numbers used to count objects. Okay. Next up are our integers. So our integers are numbers like -2, -1, 0, 1, 2, and so on in both directions. Okay, so these look very similar to the whole numbers. The only difference is we now add in the negatives. Okay, so we say that integers are positive and negative whole numbers. All right, so we're going somewhere with this. There's a reason we're doing this. It'll all tie together in a second. All right, next up, rational numbers. Rational numbers are numbers that can be written as a fraction. So like 1/2, for example, can be written as a fraction. So any decimal that ends can be written as a fraction. So like -0.78, for example. Whole numbers can be written as a fraction, right? I could put it over 1. Okay, so those are some examples. And again, we say these are numbers that can be written as a fraction. Okay, so think about those as decimals that do not go on and on forever. Next up, irrational numbers. So irrational numbers do go on forever. So these are things like the square root of 2 or pi. We've talked about the number e before as an irrational number. And we say these cannot be written as a fraction. Okay, so what we're going to get at is what types of solutions do we see? Okay, so we've got 3 parabolas here, and I want us to determine what type of solution there is. So when I look at this first one, I'm looking for x-intercepts. I do not see any. It never, ever, ever touches. But the fundamental theorem of algebra tells us that all parabolas have to have 2 roots, or 2 solutions. So because it never, ever touches the x-axis, right, I can't say, it touches at 2 or 3, for example. That's my solution. That means that we have something called imaginary solutions. Okay, so I can't see it touching the x-axis anywhere. So we say that there are 2 imaginary solutions. Okay, so this next one, let's think about what the solutions are. I see solutions or x-intercepts here at -2 and at 1. So I'm going to look at what type of numbers is that. Well, 1 and -2, those are integers. So I'm going to say 2 integer solutions. All right, next up. Well, when I look at these, I can't exactly tell what those solutions are. Here and here, right? They're not integers. So we are going to say that they are irrational numbers. These are numbers that are going to go on forever. So we say 2 irrational solutions. Okay. So this right here is what you're going to be looking at for the set. So the set's going to kind of bring this all together. So for the rest of the class, then you're going to work on the set, which is on pages 56, 57, and 58. So I'll kind of run that through for you. So page 56, this is how all of them are really set up. So I look at number 8 here. All it's asking is to identify the set to which the roots of each quadratic function belong. In other words, what type of roots are there? So I look here. So first you want to think about, okay, what are these x-intercepts? Are they whole numbers? Are they integers? Rational numbers? Is it none of them? Okay, so that's why we looked at this types of numbers. So you can go back and look and match that up. Okay, so some of them might be at nice, beautiful points. Look at the next page here. Some of them they did not give you a graph for. So for example, 10 and 11. So if that's the case, you are going to go to Desmos and type in your equation, and you can look at a graph in Desmos to determine. So really, guys, these are all multiple choice based off of you looking at the graph if they gave it to you already, or typing the graph into Desmos. Same with 11, type it in. 12, they give you a graph you can see. On the next page, 13, you have a graph. 14 and 15, you'll need to type into Desmos.